Good morning, class. This will be our last lecture on the course. So before we proceed with the main conceptual application of this lecture, I'd like to discuss to you the strength reduction factor based on the old ACI. Okay. So anyway, I will be presenting to you a newer version of this, but since it requires some advanced concepts on uh, reinforced concrete behavior, so I will just be focusing on this quite old provision in the code. So we will be dealing with the strength reduction factor, focusing more on the column behavior. Okay, so let me first okay, so this is the um, the pure axial compression that we have been uh, talking a while ago on our previous lecture, but we will be concerned more on the combination of these four. Okay, so this is now a combined axial and bending. Okay, so there will be a transition between these two values wherein a member may be behaving in between uh, a column and a beam behavior. So when the uh, axial loads are not present, so it's a beam. So this is actually a beam problem, and this is a column problem. So it depends whether the column is spiral or tied. Okay, so this is for tied columns. So it can start from 70% to 75%. But the thing is, what if the member is behaving in between, meaning to say it behaves somewhat like a column, at the same time it behaves somewhat like a beam. Okay, for this we excuse me, we are now going to use this provision for code to attack the problem. Okay, so it says here that for other reinforced members, your phi value shall be permitted to be increased linearly. Okay, it's a straight line from a value to 0.90. And what is that value? So the value is will begin as VPN decreases from PV. Okay, so this PV here is simply a choice between 10% of FC prime AG or VPB. whichever is smaller. But you will notice, class, that phi here is still unknown, so we cannot use phi PB. The problem is this is still known, so we might as well use this value only, and this is backed up by this provision in the code, wherein if these provisions here are satisfied, then it is permitted, okay, to increase your fee to 0.90 as VPN decreases only up to 10%. So dito sa requirement na to, wala na yung VPB. Okay? And this is what we are going to apply here on this particular derivation. Okay, so this is now the graph of a beam behavior. So this is a pure, okay, a pure beam behavior, and this is a pure column behavior. Okay, so it depends if it's a spiral or a tide. So the line can actually be linearly going downwards straight, or the dotted line there which represents a spiral. So these others here represents other types. Can be a tide confinement. Okay, so if you look into the equation of this line now, this equation gives you actually this line here. And if you look at this equation, okay, so it's just a ratio and proportion, no? It's just a matter of subtracting. Okay, so if this is your VPN, so you have a value of P somewhere here. Okay, so this is phi. So it's just like for the spiral, it's just a proportion on phi minus 0.75. Okay, all over this now is the triangle, phi minus 0.75 all over VPN minus P, okay, is equal to 0.90 minus 0.75 all over PP, or simply this is actually reversed. Okay, PP minus PP. Okay, where PP, as I've told you a while ago, is simply 0.10 F prime CH. In the absence of a value of phi, we cannot use this phi PB, so we can assume that P phi is automatically 0.10 F prime CH. So it's true with this equation here, wherein your phi minus 0.70 all over P phi minus VPN is equated to 0.90 minus 0.70 all over P. Okay, you just solve for the value of phi in this equation, and it will yield to these two sets of formula. Okay, so we're going to use this now applied to our next topic, the column interaction diagram. Okay. So as I have mentioned earlier, the newer strength reduction factor is quite different. So it has a different value. The old value of this is 0.75 and this is 0.70. Okay, for others, the shear torsion, you just compare it, but this is basically the same. I think this is 0.85. Bearing of concrete is 75 and 85. Okay, so this is 75 and this is the same. Okay, note for the sections in which the net tensile strain in the extreme tension steel at nominal strengths between the limits of compression controlled and tension controlled systems. So we have two systems here that is actually mentioned in which I cannot explain to you very clear the derivation of this phi value because we need to still understand this concept. But again, if you want to make use of this, we just plot it, okay, and make a ratio and proportion on the basis of these values, okay, for spiral, the dotted part, and for the tide, or the other confinement type, we have the solid line, okay. So the equation of phi is based on the uh, tension strain, the net tensile strain, epsilon t. Okay, so this is the formula of this line here. We're not going to use this in our creation of the column interaction diagram. Okay, let's now move to our main agenda for this lecture, and this is the column interaction diagram. So what is this diagram for? This is just a plot of a certain curve that is basically used to analyze and design axial flexural members. Okay, so it's simply a plot of the Pn versus Mn curve. So if you will look at this figure here, the Pn axis is this one, and the Mn axis is at 0. Okay, so it's here, Mn. And the diagram, we have two diagrams here, but I want you to focus first on this red diagram here. Okay, so this is the CID that I'm talking about, column interaction diagram. Okay, so there are at least 5 critical points that are needed to plot the curve, and those are point 1, so this is the first point, point 2, second point, point 3, third point, point 4, fourth, and the fifth point is actually this one here. Okay, so we have actually solved this point 3 here, so we are familiar with this. So these are the balance condition or balance parameters for the CID. Okay, Okay, so the first point is actually the maximum it is the maximum allowable axial load, or simply the maximum axial load capacity that is allowed by the code, and it has a value equivalent to 80%. Okay, so this is 80% of your PN. Okay, so your PN max is 80%. And for point 2, it is actually at the level of the PN max, or the P max, but it has an eccentricity called the minimum eccentricity, which is actually the reciprocal of the slope crossing the interaction diagram. So normally M minimum here is unknown. Okay, so we unknown. So how do you solve this? You just uh, uh, use P max and solve for P M minimum. It's called M minimum because this will give you the minimum eccentricity that is allowed for an actual load capacity to occur. Okay, so when it is within this minimum eccentricity, then your column will behave just like a pure actually loaded column. And for point 3, we know that this is the balance parameters. We solve this by simply taking the summation of moment about the plastic centroid is equal to M. Okay, and point 4 is actually a pure beam problem. So this is the same as your pure flexure because your P is equal to 0. Okay, so this is just a pure beam problem. And point 5 is simply a problem wherein PT is the tensile capacity. So in this particular computation, we always assume that the concrete cannot resist tension. Okay, so by doing so, what's your PT now? PT is simply equal to AST minus Fy. So that's the value for your P tension. Okay, and then you can plot the curve the way by connecting this. Okay, so by a straight line maybe. Okay, so it's something like this. But there's a better way on plotting the curve, is simply by iteration. Okay, so how do we do the iterative approach? Okay, so by way of giving you an example now, I will be giving you this guide for you to be able to solve the iterative approach. What is the iterative approach? We simply assume values of C, the distance from the extreme compression fiber to the neutral axis, and compute for Pn, Mn, and E. Okay, this is done usually using a table solution in Excel, and the table may be formatted from the determination of the balance parameters PB, MB, and EB which is shown below. So if you still remember your lecture on how to deal with PB, MB, and EB using an Excel solution, then you just change the subscript into MN, PN, and E. Okay? But of course, you better check first if your solution for the Excel program is does not give you any error. No? Okay, by solving it manually. Okay, note that by simply changing the value of this balance condition here to any value, the corresponding values of Pn, Mn, and E may be obtained. Okay, so it's just like substituting, let's say 50 here. I just change this 50 and everything will be solved. No, so this is now a negative. Okay, so the parenthesis here, class. Okay, so the parenthesis means that's a negative. Parenthesis is actually negative. Okay, so these are negative values. So you're at 50, your point is somewhere located on the graph, somewhere at the tension side. So dito yon, no? Banda dito. Okay. Of course, you cannot plot it just by using 1 or 2 points. So you have to do the iteration uh, by using several points. Okay, I actually separated here to make it a little bit bigger. And upon doing so, we just take the summary. Okay, I started actually at 10. All I need is to substitute 10, 50, 70, 80, 90, 100, 150, 200, 250, etc. Okay, up to about a value. So where do I stop? So I actually stop at a value more or less twice your age. Okay, so this is twice the, almost twice, or can be less than, more than, or less than twice the height of the beam, of the column. Okay, so take note, I just get my Pn and Mn and then my E. Okay, so these are the ones that are computed, and then I compute my phi on the basis of the ACI 99. Okay, so this is an old, we'll use the old ACI. Okay, so why is it that there's a phi computed and a phi there? Because taking a look at the formula here a while ago, you will notice that there's a limit for the value of phi, which is 90 and 75 only. It cannot actually exceed 90, and it cannot be less than 70 or 75. Okay, but since we are using a tied column, so we better fix it to 0.70. So if you look at the comparison now, whenever I have a value less than 0.70, I use a 0.70. Whenever I have a value greater than 0.90, I use 0.90. Okay, so you'll notice this. Okay, so greater, greater, and then this is acceptable. Okay, so acceptable. Okay, so this is less than 70, so it must be 0.70. Isa lang yung acceptable within the range, no? Okay, so you'll notice that only one value of p is acceptable within the range. And this will, what is the effect of this to the graph? So the effect is it will create a jerk on the graph. Okay, so it will create a jerk here on the graph. So where's the graph? Okay, so here. So take a look now. So the jerk is this one. This is the one that affected your phi. Okay, so phi is 0.79. Okay, somewhere here is your phi. Okay. So let's look. Is it point? So yes, 0.7. So this jerk here simply means that there's a transition on the value of phi. So transition from column to beam, or beam to column if you want, no? And this is the reduction. You call this now the CID, the column interaction diagram, and you call this the reduced column interaction diagram. So here the reduction is 70%, here the reduction is 90%. Okay, quite a big, a small reduction here, but a bigger reduction in capacity here. Okay, so if I now have a column interaction diagram, I simply if MU, PU, and MU and PU are given, okay, so if they are given, then I just plot it. If my MU is say here, this point, and my PU is here, I just make a plot. Okay, my point is there. Then it is inside the curve. If it is inside the graph, then save. Then my design is safe. Okay, so if my graph fell somewhere here, MU I mean, and this is PU. Okay, so my graph now outside the graph. What graph I'm referring to? The reduce. Okay, so then the design is unsafe. So that is the meaning of this graph, the column interaction diagram, when it comes to the analysis of columns. Okay, so thank you very much for listening. I hope you have learned how to do a plot of the column interaction curve, because it will help the designer, okay, interpret his or her design very efficiently when it comes to actual flexural members. Okay, so thank you for listening.